Hi everyone, welcome back to another lessons learned video. Today we're going to go over glycolysis and how you can use some organic chemistry knowledge to understand why the reactions in it occur, and maybe that'll help you memorize some of the names of the molecules and the enzymes. So let's first begin with the molecule we're inputting into this process called glucose. So I have basically highlighted every carbon in orange. So glucose starts out with 6 carbons, and if you number them, this guy right here is the first carbon. It also happens to be the anomeric carbon in glucose. And if you number them, you can see we get to 6. So conventionally, they're numbered like this. The anomeric carbon is the carbon that attaches to this little like oxygen in the middle. Okay. Now, the first step is catalyzed by an enzyme. I covered the enzyme in like a little box. So hexokinase is the first enzyme, and it takes 1 glucose, 1 ATP, and the way you can tell it's ATP is because the adenosine part is here, and then you have 3 phosphates, so triphosphates, and takes one of the phosphates off of ATP and puts it on the number 6 carbon. So the number 6 carbon has a phosphate. A phosphate is just a phosphorus with a few oxygens around it. Okay. And the result of that first reaction is glucose 6-phosphate. Pretty straightforward, I think, so far. Then this same molecule goes into another reaction, and this one is catalyzed by phosphoglucoisomerase. Now, isomerases, at least this isomerase, basically take the same atoms and they just rearrange them. So in the product of this reaction, which is fructose 6-phosphate, you can see how we have the same number of carbons. This time they're numbered a little differently, but I'll explain that. But you have the same number of oxygens, same number of hydrogens. You still have 1 phosphorus in this little phosphate. Now, the way you number a fructose, this is a fructose, that's a glucose. The way you number a fructose is a little different. You actually start here. That's number 1. Number 2 happens to be the anomeric carbon. So in glucose, number 1 was the anomeric carbon that was attached to this oxygen. Here it's number 2. Then number 3, 4, 5, and the 6th carbon, and the phosphorus is attached through an oxygen to that 6th carbon, which is why we call it fructose 6-phosphate. And so we're just changing the arrangement of the carbon atoms in this molecule. So it's really an isomerase. It doesn't really add or subtract anything fundamentally from the molecule. And by the way, a kinase is a molecule that transfers a phosphate. So transfers a phosphate from one molecule to another. So in this case, it transferred it from ATP, put it on a glucose. Okay. So now we have fructose 6-phosphate. We're going to have another enzyme called phosphofructokinase 1. Sometimes it's called PFK1 as well. This enzyme puts a phosphate, takes an ATP, takes one of its phosphate, puts it on number 1 carbon. So the result is fructose 1,6-bisphosphate. So instead of having 1 phosphate on a fructose, you have 2, and the second phosphate that we added is on the number 1 carbon, and the one that was originally there is on the number 6 carbon. Okay, that makes perfect sense. Now, the next enzyme is called an aldolase. It breaks the molecule into 2 pieces, and the way it does that, you can almost kind of see it here. Imagine cutting this bond and then cutting this bond, right? You get 2 pieces. You get this piece that I'm going to highlight in this violet color, whatever this is called. And this little piece is going to turn into these carbons. So you can see how the middle carbon is normal. The one on the side has a phosphate. And so the one on the side here has a phosphate. And in the other case, the orange ones, these carbons turn into these carbons, and the one on the side also has a phosphate. Now the names of these molecules, this one is called glyceraldehyde 3-phosphate. Okay. Now why is it called that? Glyceraldehyde, if you write it out, write it out in the same color. All right. Glyceraldehyde. You see that aldehyde part, right? There's an aldehyde group right here. Also, if you start numbering at the aldehyde, which is conventionally what's done, the number 3 carbon has a phosphate attached, so the 3-phosphate also makes sense. All right. The other molecule, the DHAP or whatever, it stands for dihydroxyacetone phosphate. Now, let's focus on the A part, the acetone. Acetone is this molecule right here, right? And so this looks kind of similar to an acetone. You have the middle part, you have the 3 carbons and the little ketone on it. Now, the dihydroxy part, what does that mean? Because there's a dihydroxy. If you add 2 hydroxyl groups, meaning 2 hydroxys, to this molecule, you get this thing, right? And so you're starting to see this looks pretty similar to that. The only next thing we need to add is a phosphate. And the phosphate, you just replace the hydrogen on one of those hydroxyls with an actual like phosphorus and extra oxygens, and you get the same thing. So the phosphorus stands for this guy. The acetone part is the fact that there's a ketone in the middle, and the dihydroxy part is the fact that we have 2 oxygens on the sides. And should probably keep the name of the molecule at least. Okay. Hopefully that made sense. Now, most of the dihydroxyacetone phosphate gets converted into glyceraldehyde 3-phosphate through an enzyme called triose phosphate isomerase. Triose meaning 3 carbon sugar, phosphate meaning that has 1 carbon. Isomerase, again, just like the last case we saw in isomerase, it is, if you look at these molecules closely, they are not terribly different. You know, they have 3 carbons. Each of them have an oxygen attached directly. They both have like a carbonyl group, and they both have a phosphate. It's just that we're shifting the carbonyl to this guy and the alcohol to this guy, and we get this result. So fundamentally, we're not changing a lot, which is why it's called an isomerase. Okay, hopefully that makes sense why that's called an isomerase. The next step, because we broke aldolase down into 2 molecules, and then we converted most of DHAP to GA3P, you actually have 2 glyceraldehyde 3-phosphates now. You have 2 of these guys. Okay. Now, this next enzyme called glyceraldehyde 3-phosphate dehydrogenase. Whenever you see a dehydrogenase, typically you are reducing or oxidizing something. Reducing and oxidizing something. Now, this step, as you've probably heard, generates NADH. And then it turns the glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. Let's go through in detail how this happens. Okay. So, let me erase these. What is an NADH? You might wonder. If you look at NAD+ and NADH, they're not terribly different. The only difference is that NADH has this little part attached. It has 2 electrons in this little bond, and it has a hydrogen proton. So really, you can think of NADH as just the NAD+ and a hydrogen with 2 electrons, right? And a hydrogen with 2 electrons is really just a hydride. Okay. Now, over the course of this reaction, you added a hydride to the NAD+, and you made it an NADH. Where do you think that hydride came from? Look in this molecule. Where do you see a hydride that could easily be detached? If you look closely, you'll notice this little aldehyde part. that little aldehyde part in the product is changed to a phosphate. Meaning essentially what is happening is the enzyme sort of takes a phosphate. So let me draw a phosphate real quick. So that's just a free phosphate that I drew. It has the oxygen of the phosphate, one of the oxygens, attack this carbon. And then this whole hydride leaves and joins the NAD+. So this way you are adding, more electrons. You're adding a hydride to the NAD+, so you're reducing the NAD+ to an NADH. And then you're oxidizing the carbon that is here. And you can see in the product how the phosphate is attached now. Okay, so that is why in this reaction we end up with a product that has two phosphates. So the original phosphate that was attached to number 3 carbon and the new phosphate on carbon number 1. And that's why this is called 1,3-bisphosphoglycerate. All right. Now, and of course, this carbon here being 1, 2, and 3. Now, phosphoglycerate kinase is a cool enzyme. Again, we said kinases are going to transfer phosphates to other molecules. In this case, we actually take, let me show you, we take this phosphate and we attach it onto an ADP. And we get an ATP. And then as you notice, since we took the phosphate off, the phosphorus is gone, we just have a normal carboxyl end. And so instead of 1,3-bisphosphoglycerate, we have 3-bisphosphoglycerate. I'm sorry, 3. Instead of 1,3-bisphosphoglycerate, we have 3-phosphoglycerate. Okay. Now, something to notice here. We had 2 GA3Ps, right? And we have, my pen died. Yeah, I can't use my pen. As my Apple Pen died. So now that it's recharged, I wanted you to pay attention to the fact that we had 2 glycerol had to be phosphates. Therefore, we created 2 1,3-bisphosphoglycerates, meaning we technically generate 2 ATPs in this step. All right. And we are at 3-phosphoglycerate. Now, a mutase is similar to an isomerase. We're not necessarily rearranging carbons. All we do is just move this phosphorus to this other oxygen, and the hydrogen goes to the other one. And as you can see in the product, that is what happens. We go from a 3-phosphoglycerate to a 2-phosphoglycerate. Okay. Then, the enzyme that catalyzes this step is called enolase. And it's an interesting mechanism because if you look at the reactant and you look at the product, you're like, okay, you can think to yourself, something happened, right? And you can see how there's a water that left. So you can start to think, okay, look, maybe, just maybe, there was a hydrogen here, and perhaps some sort of base. We don't know what base the enzyme uses. At least I don't know. But some base from the enzyme probably nicked off this proton. The electrons fell onto between these 2 carbons, and that pushed out this guy. And so what you can see is that we stole a proton and a hydroxide, which then combined to become this water molecule that we lost. And then there's another set of electrons. These 2 electrons fall here, and you form that double bond, as you can see in the product. Okay, so it is really a dehydration reaction. Now, this molecule here, if you remember Orgo-2, does this look familiar to you? Right? It may not look obvious at first, but let's try and think back to something like this, right? What is this? Do we remember what this is? So this thing is called an enol. It is when you have a double bond, and at the end of a double bond, like directly on that carbon, there's a hydroxyl group. Now this thing isn't exactly a enol, because it kind of looks like it when you look here, but there's a phosphate attached. So we call that a phosphoenol. And the name of this molecule, as you'll notice, is phosphoenol pyruvate, for that reason, because there's a enol part and there's a phosphate attached. Okay. Now, the next enzyme is called pyruvate kinase. And again, we have two of each of these. So I should really mention two of this, two peps. Okay. In every little thing, we have two of it. Pyruvate kinase, which is the last enzyme, it basically nicks this phosphate off and gives it to an ATP, and you get gives it to an ADP, and you get an ATP. Now, what happens if you take that phosphate off? Let's think of it, right? If you take that phosphate off, you'll have to replace the phosphate with a hydrogen. Okay, let's try that. So let me redraw the molecule. Let's say you take the phosphate off, and yeah, it's going to be awkward if I copy the arrow. Okay, we took the phosphate off. It's now on the ATP, and we have this. So now it is an enol. It is not a phosphoenol. It is an enol. Remember back to Orgo 2 again. What happens to enols, right? What do they tend to do? Right, if you have this guy, for example, what does he do? They like to tautomerize into ketones or aldehydes. So in this case, you'll see that if you have this molecule, it'll spontaneously turn into this guy. It'll make itself into acetone. Okay. So that's called keto-enol tautomerization from Orgo. If you have this guy, what does he naturally turn into? Right, this little enol turns into a ketone, and you get this guy, and that is the exact same thing as acetone. So that is the last step there. It uses keto-enol tautomerization. All right. Now, I know that many of you probably don't remember all of this from organic chemistry, and that's understandable. But if you do, it really helps to understand why these reactions happen, and helps you to sort of make sense of the names of the molecules and the names of the enzymes. Because fundamentally, if you just focus on the underlying reactions, the names kind of should come naturally, or at least more naturally than they would if you just try to rote memorize it. So let's do a quick review of this. So kinases add or subtract, phosphates. They transfer molecules to different molecules. They transfer phosphates to different molecules. Is the best way to say it. So here, you just take one from ATP and you give it to glucose, and you get glucose 6-phosphate. Then you isomerize the molecule, so not much of a change besides just the arrangement of carbons. Then you add another phosphate to the molecule. Okay, you get the little bisphosphate, 2 phosphates. You break the molecule into 2 pieces, and then those 2 pieces become 2 glycerolide 3-phosphates. You do a little oxidation reduction where you sort of use Ga3p dehydrogenase to get some NADH, and the way you do that is off of the aldehyde of glycerolide 3-phosphate. And then you have another kinase step where you make 2 ATP because you're taking the phosphate of this guy, giving it to ADP. Then a little mutase, so similar to an isomerase, you just move this phosphate to the other oxygen. Then in this step, you do a little dehydration with deanolase where you create a double bond. And then it becomes a phosphoenol, which is why it's called PEP. And then if you nick the little phosphate into an ATP, it becomes a normal enol, which will become a ketone and becomes pyruvate. All right, I hope that helped. Again, if you don't know the underlying chemistry or you forgot it, I don't know if learning it would be worthwhile. Perhaps just focus on memorizing the names of the steps. But at the very least, I hope this helped you make sense of some of the orgochem behind glycolysis. Thank you for watching.